We continue the afternoon session with a lecture by Professor Shikma Bressler from the Weizmann Institute. As we discussed, Yuval started particle physics, high-energy physics in Israel, and he hired some experimentalists, and he made a big push to develop the subject. And Shikma is a member of the generation of the current leaders of this effort, and she will tell us about the present and the future of experimental high-energy physics in Israel.
Yeah, so thank you. I'm honored to be here to speak in this event. I was asked to discuss future directions in experimental high-energy physics in Israel. Just to say that we are talking about the current step in a journey that started long ago, trying to understand what are the fundamental building blocks of the universe, with the periodic table of Mendeleev that shows that all the different elements are basically consisting of the same sub-particles, which are the atoms. And basically, we try to look deeper into smaller length scale or higher energies to dig into the atom and beyond. We know, as far as we can tell by now, by the theories and all the experiments confirm that so far, that the electrons, for instance, and the quarks that were mentioned here earlier many times, are to the best of our ability to measure our point-like particle, and we are able to measure down to 10 to the minus 18 meter. And this is a late talk, I hope so. Just to say that 10 to the minus 18 meter means let's take 1 meter, cut it into 10 pieces, we are left with 10 centimeter, cut it again to 10 pieces, we are left with 1 centimeter, and the third time take us in 3 orders of magnitude from 1 meter to 1 millimeter, which is a huge reduction in length. And think about doing this procedure 18 times to try to understand how small lengths we can actually measure. This was also shown earlier, so this is our current understanding of the fundamental particles, and we also know by the standard model of particle physics how these particles interact with each other. There are several groups of particles that differ by the way that they interact under the different interactions. So we have the strong interaction mediated by the gluon over there, we have the electromagnetic interaction mediated by the photon, and then the Z and the W's, which mediate the weak interaction, and the Higgs, which was for many decades the only missing piece in the puzzle, is the particle which within this model are responsible for giving the mass to the other fundamental particles. So I want you to remember these 3 groups, so the 3 types of particles, so the quarks, which were mentioned, the gluons that hold them together later on, and the W boson, when I try to discuss the following. So we know now that it was also mentioned here earlier that the quarks do not appear in nature as individual particles, but they form bound states. This is one of the main properties of SU3. And these hadrons can have different types, ones that we call baryons, the other mesons. The baryons, where we see the neutron and protons, are actually a grouping of 3 quarks, where the mesons are a group of a quark and an antiquark. And you can see here that the proton consists of 2 up quarks and 1 down quarks. What holds them together are those, according to this interpretation, at least, and this fundamental understanding, are the gluons. Such that when we think in a collision of 2 protons, like what we do in the Large Hadron Collider, for instance, when we want to look at the process where out of the collision of 2 protons we get a W boson, which is one of the bosons that are mediating the weak interaction, and another quark. What we actually have, we start from a collision of 2 protons. The protons themselves are the combination of quarks and gluons, such that what actually collides are not the proton, but the partons that made them. So in this particular case, a quark and a gluon. And in this diagram, we see that 2 quarks actually emit a W, and then the quark and the gluon interact to create another quark. And the W itself is not stable, meaning that after a very short time it decays, in this particular case, to a quark and an antiquark. But then when we as experimentalists try to measure such processes, we need to distinguish between two things. So we know that we collide two protons, and eventually we know that we measure in the detectors two quarks and a single antiquark. They form jets later on. What needs to be understood, and I was asked that earlier, that everything that happens in the middle is basically how we interpret this particular process. Actually, it's a leading order understanding of that. So there are other diagrams that contribute to the same procedure. But the interesting thing, and to me, the magical thing in this standard model and in particle physics in general, is that the standard model gives us a very strong tool to calculate precisely, for instance, what is the probability that if we collide two protons, we actually get exactly these three quarks at the end, and what are the angular distribution, etc. And then we can go on measuring all these properties very precisely and check whether this description of the phenomena actually give us eventually the thing that we measure. And so far, everything is very accurately working to the level that the level of uncertainty that we have on the theoretical calculation, taking into account together with the level of uncertainty that we have on the measurement, things are matches almost precisely. So what does it look like in real life, or an illustration of real life? The CERN Large Hadron Collider start by boosting and accelerating two protons. So we'll go on into another level of acceleration, out of which the bunches of protons are sent in different directions into the Large Hadron Collider. When we go down into the LHC tunnel, this is what it looks like. And then when we accelerate the protons to sufficient energy at the center of mass, we can actually start thinking of them not as individual hadrons, but to think of them as their constituents, which, as I told you earlier, are those particles that collide. Here is a collision, illustration of a collision at the center of the Atlas experiment. Maybe a W boson was created, maybe a Higgs, and then it decays, and what we measure at the detectors themselves are those stable particles that do not decay to something else. So this is what it looked like from the Geneva area landscape. This is the LHC. Of course, the tunnel is 100 meters underground. At the center of one of the collision points, the Atlas detector exists. It is 46 meters long, about 25 meters in diameter, 100 meters underground, 7,000 tons, blah, blah, blah. Very, very, super sophisticated system. This is just to illustrate the size of a human being next to it. But why is it so challenging? And this is normally, I wouldn't put such a plot in a late talk, but what it shows is that the probability is that in a collision of two protons, something will happen. This is the y-axis. As a function of the center of mass energy collision, the LHC is roughly, well, now it's here. And what we can see is, and I ask you to focus on the left, on the y-axis basically at the left. We see that the probability that the collision will happen, here marked with 10 to the 8, whatever the units are, it doesn't matter at the moment, but you can see that processes of interest to us will happen at the probability of 10 to the minus 4 or 10 to the minus 3. That means that there could be about 12 or 11 orders of magnitude difference between the probability that something happened in a collision to the probability that the thing of interest to us will happen. And that means that if we want to measure these processes, we need to create at least 10 to the 12 collision. And actually, we need a lot more because we need enough statistics to find them. And that makes this huge gap is what makes the LHC so unique and future colliders as well, because not only it provides a lot of energy, but it also provides tons of collisions. So many collisions that we do not collide one proton on one proton, but bunches of 10 to the 11 protons on 10 to the 11 protons, about 40 million times each second for several decades. This is the amount of collisions that we need in order to be able to see processes at this probability or below. And this, of course, poses huge challenge on how we measure things. In particular, we cannot measure and we cannot store to disk all the outcomes of all these collisions. In fact, out of 40 million collisions a second, we can store to disk about something in between 1,000 to maybe slightly more. And that makes huge, a critical thing to be able to select in real time those events out of all the collisions that are actually has the potential of holding the physics of interest that we have. And I'm happy that Yaron is here because he was one of the pioneering who developed those methodologies. And this is a cross-section of 1/4 of the Atlas detector. Pay attention to the TGC, thin gap chambers in the outer region over there. And what they found out is that a potential interesting event will be an event that has high energy muon in it. Why? Because the probability or the processes in which we can get in a hadron machine a muon are relatively rare, and an energetic muon would mean a potentially interesting physics. So how do we find out in real time whether an event a collision contains a high energy muon? So this is very simplified attempt to explain that. So a super energetic muon will have an infinite momentum, and therefore it will barely be deflected or not be deflected in a magnetic field which exists in all this area, and therefore it will fly from the interaction point to the TGC station in a straight line. On the other hand, a low momentum particle, a low momentum muon, will be deflected by the magnetic field, and if it has an opposite electrical charge, it will be deflected on the other direction. And therefore, if we measure a hit, a single hit at the outer station, and another hit in this window that is defined by these two tracks here, we can tell that this particle has sufficient energy and mark this event as potentially interesting. This worked very well, except that for a long time we marked many events and thought that they have high momentum muons, but they didn't have such a high momentum muon. This is the system before. The system that was built before, I think that I joined the group toward really the end of the production of these big wheels. These are wheels produced, the majority of them in Israel. Yaron can tell you everything about it. So he invented it, he developed the entire machinery that allow, coming up from the idea of measuring muons into building such a massive system, highly non-trivial task. These are 25-meter diameter circles. But as I told you, when we started taking data, it turns out that many times we pick events in which we think we have a high momentum muons, but we don't. And what a study showed is that because of the magnet that is located here, this end captorate, these are massive material. It absorbed a lot of energy and could emit it spontaneously. So if, for instance, we have a proton that is emitted from this point, it will fly straight. And since there are so many like them, the probability that part of them will appear to us as if they are coming from the interaction point is sufficiently high. And then, even though it's not a muon, we mark it as a muon. And then the idea came out to basically add these small wheels to upgrade the detectors that we have here and include them in this trigger selection, such that no longer protons, for instance, emitted from the end captoroid will confuse us to be muons. And this is the new small wheel. We call it small wheel because it's only 10 meters in diameter. There was a huge challenge develop a different technology that can measure very precisely also this particle. It needed a lot of precision and also be sufficiently tolerate to the extreme high radiation that these chambers are exposed to. This project was completed, and the wheels are now part of the Atlas taking data. I just don't want to confuse you. There are tons of challenges related to this project. Not everything is working properly. Far from it. We have a lot of, as a collaboration, a lot of work in order to make everything working as good as we can. But that was a huge milestone to lower down those wheels. And now, as the last upgrade phase, we are working on upgrading also the detector in this area, calling the inner end cap inner layer 4. You can see this is from the current production lines that we have at the Weizmann Institute. And these are the first detectors installed in the Atlas cavern as a test to see that we know how to replace those chambers. So future projects. First of all, just to give you a brief idea. So the LHC, which collected the data that we are now analyzing, the idea to build this LHC conceived something at 1980 or so, I guess. And we are now analyzing the data based on the machines that was considered and developed and designed decades ago. That means that if we want to be able to take some data and analyze it 20 years from today, we need to be working now on the upgrade itself. So this started with the high luminosity LHC, which we are now in the transition to install chambers that could operate at that condition. And the community already working on future possible projects. Of course, these are huge efforts by many countries. And as Eliezer said, eventually someone will have to agree to pay for these endeavors. But just to say that in June, there is going to be a large gathering of the European community, not just the European, but led by European community in Venice, try to come up with the strategy of the community for the next 5 years, probably pushing forward for the construction of the future circular collider, just to show you how small the LHC suddenly look like when you think about a ring of almost 90 kilometers long. The LHC is only 7 kilometers long. In the meantime, in order to guarantee that we will have the needed technologies to operate a particle physics experiment in such environment, there was a decision taken about 5 years ago to form collaboration to develop detector technologies in view of what we will need in the future. So many collaborations were established. The Israeli community, we are involved with 6 collaborations out of them, giving our contribution to the development of detectors for future accelerator experiments and beyond. 8, 9, I have enough time. Of course, the European project is not the only one. China has a competing project with very similar properties to the FCC. They also need to take a decision probably this year or the next one whether they are going to push this through. The Americans in parallel decided not to build a collider experiment, instead to focus on neutrino physics with the Dune experiment and on the study of electron-ion interactions in the EIC project over there. In the meantime, before we have the future large accelerator, we are as a community, first of all, working a lot on data analysis of data collected with the Large Hadron, with the LHC and the high luminosity LHC, but we are also working a lot on detector development, but we are also involved with many smaller scale projects. Just to name some, these are not necessarily the Israeli community, but in parallel to the huge endeavors, there are tons of smaller experiments like Phaser, like NA60, Luxi, and many more. What we are focusing on are at the moment, so at the LHC and the high lumi LHC, we work on the detectors themselves, on analysis of the data. In the further future, at the moment, our activities are mostly within those detector R&D collaborations, which is aligned at the current strategic decision of the entire European community before it takes decision on what would be the future accelerator. And we are involved in many smaller scale experiments, for which we also construct detectors. I'll give you a brief of the youngest generation of Israeli experimental particle physicists. So Adi Ashkenazi at Tel Aviv works a lot on neutrino physics at Dune. This is the first arrival of the equipment to Air Lab to build here a cryogenic system to cool down argon. Ben Ochayon at the Technion works on novel quantum sensing technologies to work with exotic atoms. So they build atoms with muons surrounding the nuclear rather than electrons, for instance. So this is an experiment at PSI. Liron Barak, the team at Tel Aviv University, does a lot of data analysis at Atlas, but also development of methodologies to trigger more efficiently on particular particle to improve later on also the analysis potential of that parts. Zvi Citron at Ben Gurion University works on heavy ion collisions, also in the construction of what is called the 0-degree calorimeter, which is a subsystem or a detector that is installed on the far end of the LHC beam. Rani Budnik's group at the Weizmann Institute works on searches for dark matter. This is an example of the xenon experiment at Gran Sasso. Noam Talhod at Weizmann does a lot of data analysis at Atlas, but works also on the Luxi experiment, which aims at studying the interaction of quantum electrodynamics at a very high energy, the new regime of testing this theory. Lior Arazi at Ben Gurion works on detector development and also on the next experiment, which tries to check whether neutrinos have the properties of being the Majorana particles of the antiparticles of themselves in searching for neutrino-less double beta decay. Enrique will talk after me, works on first data analysis in Atlas and also on building data acquisition system for Atlas to improve the data collection, and also in the phaser experiment to check for potentially new physics that interacts with muons. And my group at Weizmann, we do detector development for future experiments. We also do a lot of data analysis. And I think that basically this is it. So I was on time. Thank you.
Much. And since Shikma, as a good experimentalist, kept to the time, we have now time for some questions. So,
yes.
Thank you very much for this lecture. My question is, what is, you think, the major discovery that is against the standard model, if there is such one?
So I would say it's slightly different. As I said, the standard model is incredible because mostly because it gives us tons of predictions of what we could search for and measure. So far, everything that it predicts and we could measure precisely enough, the agreement is at the moment, the tension is only in very rare scenarios, and we cannot claim that we see a deviation from the standard model prediction. On the other hand, and this will be the talk, I think, of Enrique later on, there are tons of things that the standard model do not explain. So in this respect, it is clear to us that it's not the end of the story. There should be something in addition to the standard model. To be honest, we have to say that everything that we thought could be extending the standard model so far has been excluded, mostly, large part of it by the LHC. But it only makes things more, more curious, I guess.
if I may add, there are two experimental facts which clearly are beyond the standard model. One is the fact that we see matter and not antimatter in the universe.
This is Enrique.
Yeah.
This is why I'm not in.
I'm not just speaking about standard.
Okay.
And for that, you need an amount of CP violation which we do not yet observe, and it's probably it is not coming from what we know to be the source of CP violation in the standard model so far. And there is a perhaps related issue of the neutrino masses, which do not fit neatly in the standard model. So, but I don't want to take any more time. So
we can also, ask ourselves, for instance, why is the mass of the electron the mass of the electron? If this is an interesting question to study, then the standard model does not explain that. And to me, this is an interesting question. And, unless you are willing to accept that there are some fundamental numbers coming out of nowhere, but then you can ask yourself, then what caused the difference in mass between the electrons and the muons, for instance, which are very, very similar apart from their masses. So all these questions, this is to me, this is the exciting thing. You can keep asking questions regardless of what, and they are very, very good questions to ask.
David, please, but microphone, please.
I'll just talk loudly.
Sorry? This is broadcast, also in the college.
No, just just a question you might not want to answer. How many, you might not want to answer this, how many low sigma deviations do you have that you hope that high Lumi would either kill, most likely, or not?
How many?
To
I think about a handful, coming out of the 4 experiments that are running on, that are located at different points along the LHC. But for instance, I can, so what I'm writing here, for instance, we can look for bumps. We can look for new particles that should appear as bumps in our distributions. So one of the studies that my group is carrying out is to find a way to search fast for all these bumps, because we run now for, 15 years, and out of about 20,000 different possibilities, we looked at less than 10%, right? In 10, we still haven't opened the box at all.
So you still have some hope before the upgrades are.
Yes. Otherwise, I wouldn't be, measuring myself there. Yes.
So let us thank Shikma again. And